This video is an attempt to go over all the things that we've studied in AP Physics 2 in the first semester as it relates to the equation sheet. So finding all the different constants and equations that we've talked about to hopefully bring you some comfortability before you take your first semester final exam. So I'm going to go through this page by page, and the first thing that we're looking at here are the table of constants and conversion factors. I really only want to point out the things that were new that don't necessarily relate to AP Physics 1 and are not necessarily things that we've seen a lot of applications of in the first semester. So just because I skip over something doesn't mean that it couldn't be used, it just means that it hasn't really been the focus of what we've been doing. So the things that I'll point out first are Avogadro's number, the universal gas constant, Boltzmann's constant, because all three of these constants were used when we were doing thermodynamics problems and working especially with the ideal gas law. There are a couple of other equations that include Boltzmann's constant, for example, when you're finding the energy associated with a gas or individual particles. On the right-hand column, something that we've dealt with this semester as we've worked with electric force, electric charge, electric potential, electric fields, is we've used different charges. And so obviously if we're working with the charge on the electron or a charge on a proton, we need to know what that charge is. More often than not, we're just working with it symbolically, and we haven't really had to plug in that charge very often, but we do need to know where that is. And then we also need to know that if we're working with electrons, it's negative. If we're working with protons, it's positive. And I think that's more or less it for the top column there. Looking down then below that, there are a bunch more things that we've worked with. One especially that has come up is the Coulomb's law constant, because Coulomb's law constant makes its way into all of our equations for electric force, electric potential, and electric field. And vacuum permittivity, E naught, is built into K, which is why when you look at the Coulomb's law constant, it can be written as 1 over 4 pi epsilon naught. That epsilon naught is the vacuum permittivity, which is given there, E naught in the, on its own up above. And also at the bottom, we see the, a representation of atmospheric pressure, which is 1 times 10 to the 5 newtons per meter squared, or 1 times 10 to the 5 Pascal, because 1 Pascal is 1 Newton per meter squared. That was something that came about quite often when we were working with fluids and talking about pressure with various things that we did there. The box down below that, which has a bunch of unit symbols, most of these we should have memorized by now. There's a few in there that we haven't talked about yet, but things like meters, kilograms, seconds, amperes, Kelvin, should all be, well known at this point. There are a few that we haven't dealt with very specifically yet so far this year in AP Physics 2, like Hertz, Henry, Tesla, and even really electron volts we haven't talked about very much yet. But the rest of those units you should be comfortable with, and you need to make sure that when we start going over the equations that you know where those units match up with the different variables in our equations. AP Physics 2 is a class where actually some of the units we use, they're defined on a very large, very small scale, so we end up having to use a lot of prefixes when we write the units if we want to do practical problems. For example, when we talk about charges, it doesn't make sense to always have charges that are 1 coulomb or 2 coulomb, and for that reason we end up with rather small amounts of charge that tend to be represented in micro or nano coulombs. The same thing goes for some of the other units that we've dealt with. There's not a lot of unit conversions that happen. There's a little bit more in AP Physics 2 than in first year physics, but if you're ever not sure of how to convert, then the factor by which you would need to multiply to get back to the base SI unit is given here on the front table, and you need to be aware that those things are there if you need them. The table of trigonometric functions for common angles, I don't know that you'll really need to use that much, because for most of us, it's just as fast to just go to our calculator and figure out what the value of any of those are. If you didn't have a calculator, that would be very important and useful. But it also reminds us that when we're trying to use sine, cosine, and tangent, and we're given a angle that is in degrees, then our calculator needs to be in degrees. And so it's a good reminder to make sure that before our final exam, if we're given things that are in degrees, make sure our calculator is in degrees. The last table that's on the front page lists a bunch of conventions, and some of these were new to us this year. For example, number 2 says, in all situations, positive work is defined as the work done on a system. That was especially important when we were dealing with the laws of thermodynamics and the work done on a system, the internal energy of the system, and keeping track of where the heat was going. For number 3, this is a convention that we used last year. It says the direction of current is conventional current, which means it's the way that positive charge moves in a circuit. And that's the same as what we've dealt with since we first started learning about circuits. The next one says that all batteries and meters are ideal unless otherwise stated. This is good because we know at this point now that batteries can have some internal resistance, but unless they specifically state that, we're to assume that all batteries and all meters, like voltmeters, ammeters, multimeters, are ideal, which means they operate the way they're supposed to operate. And so they don't have any internal resistance, they work perfectly. Assume edge effects for the electric field of parallel plate capacitor unless otherwise stated, which means that when we get near the edge of a parallel plate capacitor, we don't get a perfectly straight electric field. There's some curvature there due to the edge of being at the edge of the parallel plate capacitor. Also, as we've defined it in class, for electric potential, that electric potential is defined as being 0, an infinite distance away from a charged object, which means as I move closer to a charged object, the magnitude of the electric potential will increase. The first page of the equation sheet includes a lot of equations from AP Physics 1. I think it's unreasonable for me to say that you're going to understand and be able to apply all the old equations from AP Physics 1 as well as you'll be able to apply the new ones, because our focus has been on the new topics, but we've also seen many cases where the old equations from AP Physics 1 can be applied in the new cases. For example, when we did fluids problems, we used the kinematic equations to study how fluids moved, because after they exit a bottle, for example, they're essentially in projectile motion as the fluid falls to the floor. And so my suggestion to you for pretty much everything on the left-hand column of this equation sheet is to go back and watch the AP Physics 1 mid-year update that I've posted for the equation sheet. And I think that'll be a good exercise because in a matter of about 20 minutes you might get a little bit of review of a lot of these equations which you may or may not have used in quite some time. My focus here now is going to be on the right-hand side, because on the right-hand side we have the electricity and magnetism equations, and that has been our focus for like the last couple of months. So first I'd like to point out at the top, the first equation is for electric force. And the electric force, the fact that the electric force depends on the product of the charges and is an inverse square law, which means it depends on 1 over r squared, the separation between the two objects squared. This is an equation we dealt with last year, and now this year we've used as well. And the absolute value bar signs are around the charges because we don't plug in the signs of the charges, and this equation does not tell us the direction of the force. It only tells us the magnitude of the force. We can always go back up to the diagram, back up to the picture where the charges are in order to figure out which way the force points, because we know that like charges repel one another and opposite charges attract. The equation below that is kind of like a definition of what electric field strength is it's the electric force per unit charge. A lot of the time we've written this as F equals Q times E, where the electric force and the electric field are both vectors. Furthermore, down below that, we have our equation for electric field, which is just Q, which is the thing that is producing the electric field, divided by r squared. If you combine the first two equations, you can see why one of the charges would drop out. We would still get the 1 over r squared relationship, but Q is the thing that's producing the electric field. and so there's only one charge there. Still, we use the magnitude of the charge Q to determine the magnitude of the electric field, and we know what direction the electric field points not from the equation, but because we know that if we place a positive charge, a positive test charge, in the region where the electric field is, the electric field points in the direction that that positive charge would feel a force. And so using that convention, we can always figure out, independent of the equation, which direction the electric field points. Below that, we have our equation for electric potential energy. We defined electric potential itself, V, as being the electric field strength times D, which is a position relative to something that's producing an electric field. And so we can plug that in to our electric potential energy equation and see that electric potential energy, U, is equal to Q times V, which is Q times E times D. And we made several comparisons between electric potential energy and gravitational potential energy, because gravitational potential energy was M times G times H. And so we replaced Q with M, we replaced E with G, and we replaced D with H. And so we made a lot of comparisons there, and so I think this helps us better understand and remember the equation for electric potential energy, but it also helps us define what electric potential is. E times D versus G times H. It's a kind of a measure of the potential for energy to be had depending on whether we have a big charge, little charge, big mass, little mass. It only depends on the qualities of the field and your position in that field. Below that, we have our equation for electric potential, which is not a 1 over r squared relationship. It's just 1 over r. And the reason for that is because of the way that we define the electric potential, E times D, if you plug in E into that relationship, you should find that one of the r's will cancel, leaving us with just 1 over r. Notice the absolute value bar signs are not there. If the charge is negative, then we will have a negative potential, and if the charge is positive, we'll have a positive potential. Which is why when we take a couple of charges and separate them, let's say a positive and negative charge are separated by some distance r, we can describe where the potential is positive and where the potential is negative, because we know things like, if we're closer to the positive charge, then the positive charge will contribute a greater positive potential than the negative charge will contribute a negative potential, and for that reason the total potential at that point will be positive. Lastly, this relationship here is essentially a different look at our definition of electric potential. If we pick 2 points that are separated by a distance r and measure the potential at those 2 points, and subtract the voltages and subtract the positions, then we can find the electric field strength that way as well. You should also be able to see the similarities between this equation and the equation that's circled up above, because electric field is still voltage divided by distance. The next equation relates voltage, charge, and capacitance. Another way to look at this is to rearrange it for capacitance, which would be Q divided by delta V, and we have thought of capacitance as being the charge per unit volt that a capacitor can store. The equation below tells us if we have a capacitor which has plate areas of A and a separation D, and maybe has a dielectric, then we can figure out the capacitance based off of those physical characteristics of that capacitor. And below that, we have an equation which tells us what the electric field would be on that capacitor with plate area A if there's a certain amount of charge Q that is stored on those plates. By combining a couple of the equations above, we could show that if we store some charge on a capacitor, then there will be some potential energy associated with the separation of charges. If there's a certain amount of charge Q and the 2 plates have a potential difference across them, then there is potential energy associated with that configuration, which is given by the equation that I've circled in green. Having made it through most of those equations, which there is a lot of information packed in that first half of this second side of this first page of the equation sheet, a lot of the equations that are below are related to circuits, whereas most of the stuff that's on the top half is related to electric force, electric field, and electric potential. So immediately, we have a couple of equations which we saw in our first year physics course, which was that the current is given by charge divided by time. A certain amount of charge passes a point in a certain amount of time. That defines the current. How much charge moves past a point in a certain amount of time. Below that is our equation that includes resistivity, which says that if I have a certain material with a certain resistivity, in a certain area and a certain length, then I can find the resistance of that material. And the resistivity is something that can change with certain parameters, but different materials have different resistivities. So if you cut a material to a certain length and a certain cross-sectional area, you can determine the physical resistance of that material. And then now that we've started to do more circuit problems again, we've seen how the power equation, which can be displayed as I times V, or with manipulation through Ohm's law, we've also seen P equals V squared divided by R. Power equations can give us insight to things like brightness or energy relationships with what's happening in a circuit. The equation that follows is just Ohm's law rearranged for current, V equals I times R. Really the thing that guides us in all of our circuit problem solving. And then following that, we have all of our relationships for how to simplify circuits by finding equivalent resistance or equivalent capacitance when we're working with multiple capacitors or multiple resistors in a circuit. These are really powerful because in order to understand what's happening in a complicated circuit, very often we need to take multiple components and reduce it down to find an equivalent resistance or equivalent capacitance, which might allow us to find a total current or a total voltage, which would then allow us to analyze individual circuit elements afterwards. Please make sure that you're not getting the rules backwards. The resistors in series add directly, but capacitors in parallel add directly. And then the 1 over equals 1 over plus 1 over rules are for resistors in parallel, but capacitors in series. You never really need to worry about memorizing these because they're all here on the equation sheet. I think that pretty much wraps it up for the first page. We don't need to worry about the second column. This includes a bunch of equations which are related to magnetism, which we haven't dealt with yet. And the first column, I wanted you to watch that AP Physics 1 video. As you get to 3 semesters into your physics career, there's a lot of equations, there's a lot of variables, and there's a lot of things to understand. And so maybe more than ever, these lists here that include all of the variables defined, it's a good job to make sure that you know what those things represent, and it's a good thing that they're there because anytime you forget what a letter might mean or a variable might mean, then you can always refer to the list to make sure that you know what it is. And if you're ever trying to write a response to a free response question and want to describe what any of those variables are, then you can always look at the list to make sure you're calling it the right thing. On the last page of the equation sheet, there are a few sections that we haven't really dealt with yet. So the waves and optics section, which will be a very exciting unit we haven't gotten to yet, that and the modern physics box here, those are both topics that we'll cover in the second semester. Then the geometry and trigonometry section, we know at this point that these types of things can make their way into physics problems all the time. I would hope at this point that most of those relationships are things that you know. But a lot of times when we're doing graphing problems or maybe different types of problems, we might need to know the area or the volume of something. And trigonometric relationships using a right triangle like sine, cosine, and tangent are relationships that are like second nature to us at this point. And so while we need to know that, I'm not particularly going to go over that. Just remember that it's there if you need it. The two units that we started off our year with this year were fluids and thermodynamics, and so this last section here is the last thing that we need to go over. The first equation is the equation for density. Density is mass divided by volume. And the second equation is for pressure, which is a force per unit area. And so there's really no need for us to go over those things. Those are things that we went over quite well, I think. The next equation that's listed there is our equation that tells us how pressure varies with depth in a fluid. So the deeper we go into a fluid, which means the greater value of H that we get, the greater the pressure will be. So one way that we've dealt with this is, let's say we're at a swimming pool. At the top of a swimming pool, there's a certain pressure even above the water. We'll call that P naught, and that is typically just atmospheric pressure. And then as I go deeper and deeper into the fluid, water has some density rho, which I've partially covered up with my circle around the H. But water has a certain density, and so that density multiplied by G and the distance down into the fluid that I've gone, that tells me what the pressure is at any point below the surface of the water. The next equation that's listed is the equation for buoyant force. Buoyant force is equal to rho times V times G, where rho is the density of the fluid, not the density of the object, but the density of the fluid, and V is the volume of the fluid that is displaced. So sometimes objects float and sometimes they sink, and so there can be different amounts of fluid that is displaced. And another very important point when you're using the buoyancy equation is the buoyancy equation doesn't tell me whether the object floats or sinks. What tells me whether an object floats or sinks is whether the object is less dense or more dense than the fluid it's being placed in. Only then can we start to understand the relationship between how much fluid would be displaced. The next equation that's listed there is the continuity equation, which we found showed that the product A times V is something that's conserved. So A times V equals A times V at any point where a fluid is moving through a space. And for example, if the area of, let's say, a pipe that water is flowing through decreases, then the speed of the fluid will increase, which makes sense. If I put my thumb over the nozzle of a hose and decrease the area where the water can come out, then the speed of the water increases. The next equation that's listed here is Bernoulli's equation, which is essentially conservation of energy for fluids. It relates, how much a fluid is being pushed on and how much the fluid has to push the fluid in front of it out of the way, to the height of the fluid and to the speed of the fluid. And so you can think of this as our conservation of energy equation for fluids. And if you think back to some of the problems that we did using this equation, we found even relationships that we found in first year energy relationships, like the speed of a fluid is proportional to the square root of the depth of the fluid, and some other relationships. And most of the problems that we did with this equation, a lot of the terms canceled out. It was just a matter of deciding where the height is equal to 0. Just like in typical conservation of energy problems, we set the height somewhere equal to 0. So one of the y's, y1 or y2, will probably be 0. And so the equation often simplifies. The next equation listed is our conductivity equation. The K that is on the right side of the equation is our conductivity constant. It tells us what is the thermal conductivity of different materials. And conductivity tells us how heat flows per unit time, which is why the left-hand side is Q divided by delta T. The other variables on the right-hand side are physical parameters of a material, like the difference in temperature across the material, delta T, the thickness of the material, and the area of the material. In addition to our thermal conductivity equation, the last 4 equations that are listed were all equations that were part of our thermodynamics unit. The first one after the conductivity equation is our ideal gas law, which can be written as PV equals nRT or PV equals NKBT, where KB is Boltzmann's constant. The lowercase n and the capital N are different ways of writing the ideal gas law, either in terms of the total number of particles, capital N, or the number of moles, lowercase n. And judging by, depending on which one we want to use, we have to pick our constants, but, N times R, the number of moles times the ideal gas constant, is equal to the number of total particles times Boltzmann's constant. And so there are different situations where you would have to use either one of those sets of constants in the ideal gas law. The equation below that tells us what the kinetic energy is of a system of particles that are at a certain temperature T, and we see quite clearly that if the temperature goes up, then the kinetic energy of that system of particles is going to go up as well. And the last two equations are equations that we dealt with when we were studying the laws of thermodynamics. We know that the work done is equal to a pressure times the change in volume, because we know if the change in that for a system, if the volume changes, then work needs to be done. And there's a negative sign out in front of that for the following reason. If I write this as W equals minus P times delta V, where delta V is V final minus V initial, then if the volume increases, that means the final volume will be bigger. If the final volume is bigger, then this term in the parentheses is a positive number, which means the overall work will be equal to a negative. And that's what we want. If the volume of a gas increases, then the work done is negative, because the gas doesn't have as much energy now. It makes sense that the work be negative. And if the volume of the gas were to decrease, which would mean the initial energy is actually bigger, then the term in the parentheses would be negative and the work would be positive. And if the volume of a gas decreases, that must mean that work was done on the gas. And so our convention, even from the first page of the equation sheet, is that if work is done on the gas and the volume decreases, then that work should be positive. Lastly, our equation here, delta U equals Q plus W, is our first law of thermodynamics, which relates the internal energy, heat, and work done on a system, where Q is the amount of heat that either enters or leaves the system, W is the work that's done on or by the system, and delta U is the change in internal energy. And so if the temperature goes up, the internal energy increases, and if the temperature goes down, then the internal energy decreases. So that is a lot of information. It's difficult to go equation by equation and try to summarize a lot of the information in a short amount of time. We've been studying these things all semester long. I've tried to give a brief reminder of what some of these things were. And so the bottom line is, if there are any equations on here which you don't feel very comfortable with, you really need to make sure that you bring that up to me and that we talk about it before you take your first final exam.